Yes, many thanks. So firstly, hello everyone and greetings from Dunedin, and in particular thanks to the organizers for inviting me to give this presentation. Now, I would like to tell you something about waves propagating on a black hole space-time, and this can be seen to be something like a model for the propagation of gravitational waves, these famous little ripples propagating through the fabric of space and time. Now, since I cannot assume that this audience is experts in general relativity, let me start with a few general remarks about what general relativity is about. Relativity is Albert Einstein's geometric theory of gravitation, which was published in 1915. And the basic idea is that the old concept of the Newtonian gravitational force is replaced by the idea that space and time are curved, and two bodies do not attract each other because there's a gravitational force, but just because they're moving in a curved space-time continuum. Now, mathematically, we unify three-dimensional space and one-dimensional time into a four-dimensional entity, the space-time, which is expressed as a four-dimensional Lorentzian manifold. And this is equipped with a metric tensor, which you can think about as being a symmetric 4x4 matrix, so an object which has 10 functional degrees of freedom. Now, once we know the metric, then we know basically everything about our space-time. Firstly, the metric tells us how to measure distances and angles, but from derivatives of a metric, we can also find what is the curvature of space and time, and we can derive equations describing the trajectories of particles and light rays. Now, we cannot quite arbitrarily choose the metric of a given space-time, but we have to find it by solving a complicated system of equations, Einstein's field equations. The rough structure of these equations is here. It's telling us two tensors need to be proportional to each other. The left-hand side can be obtained from the metric and up to second-order derivatives and describes the curvature of space-times. And the right-hand side measures the energy and the matter and energy content of the space-time in form of the tensor Tij, the energy momentum tensor. So in general, that's a complicated system of coupled PDEs. Now, in particular, if you want to describe something like gravitational waves rigorously, then it's important to include infinity into your consideration. So you should not just try to look at a finite portion of your space-time, but go all the way to infinity. At any finite location, you cannot really distinguish between some background space-time and a gravitational wave on top of it. Only if you go to infinity, then you can unambiguously define what a gravitational wave actually is by looking at the fall-off behavior of certain quantities. Now, luckily, there's a nice mathematical method to achieve this and to basically bring infinity to finite distances, and this is called conformal compactification. This consists in two steps. The first one is that we do a coordinate transformation. We replace the original coordinates by compactified coordinates. So for example, if you have a radial coordinate which goes all the way to infinity and time also being defined on for all real numbers, you can map these to new coordinates which are defined on some compact domain. But if you translate your metric in terms of these new functions, if you obtain a metric which I call G tilde, then it turns out necessarily this is singular at points that correspond to infinity. So in the second step, in order to take care of these singularities of the metric, you can rescale your metric, multiply the entire metric by a positive function. Theta is called the conformal factor. Then you can achieve that the rescaled metric G, obtained by multiplying this G tilde by this factor, that this is actually regular. And this conformal factor theta automatically needs to vanish at infinity in order to make sure that we can regularize the metric there. Here's an example for this procedure. If you look at the simplest possible spacetime, the flat Minkowski spacetime, the spacetime of special relativity, then the metric looks like this. That's expressed here in terms of polar coordinates. So this part here is just in the usual way how you measure infinitesimal distances in polar coordinates. And in relativity, we also include a contribution coming from the time coordinate. Now, initially, these coordinates are defined for all positive values for r and any real numbers for t, but we can actually map this infinite green domain to this compact triangle if we use this coordinate transformation here. So if we introduce a new radial coordinate capital R and a new time coordinate capital T. And then if you appropriately rescale the metric, you can represent the same metric in terms of these new coordinates. And after rescaling like this, where the conformal factor looks like this, and this does vanish along this boundary and along that boundary, where either this or that cosine factor are zero, so that's the points corresponding to infinity. If you look at the propagation of light rays, then in either picture, they follow straight lines at an angle of 45 degrees, lines with slope plus or minus 1. If you look at outgoing light rays, they follow such lines, and ingoing light rays these lines, and the same is true in this picture. So in particular, any outgoing light ray would eventually arrive at this boundary, and if you trace back incoming light rays, they would eventually have emerged from this boundary. So these boundaries are also referred to as null infinity, because light rays propagate along so-called null curves, or as sqi minus and sqi plus, using this notation here. Sqi is just an abbreviation for the script I, so just this particular symbol used to express this. So sqi minus is where all light rays emerge from, or any gravitational radiation that is ingoing into your space-time, and sqi plus is where all the information eventually ends up, and where you could rigorously define gravitational waves. And right in between these two boundaries, here we have I0, which is space-like infinity. That's where all the space-like geodesics would end up. Okay, now it's well known, this space-like infinity, this point in this previous diagram, introduces certain mathematical difficulties because various functions tend to develop nasty singularities. And there typically we find some sort of singularities near this point, which are called space-like infinity. And in order to better resolve these singularities, it's useful to replace this point by an entire cylinder. So there's a well-defined procedure to blow up this point into a cylinder. And then we obtain something which is of topology S2 times the time interval. And S2 just refers to the angular degrees of freedom theta and phi. So in this way, we can better resolve these singularities. And this cylinder somehow connects past null infinity sqi minus and future null infinity sqi plus. Now, in order to understand how fields behave, in particular in the vicinity of this cylinder, and as a basic model for the propagation of gravitational waves, I don't quite want to solve the complicated full Einstein equations, but instead I look at this equation here, which is called the conformally invariant wave equation. It's a wave equation for a scalar function f. And here, these are just second-order derivative operators. So that's just the version of the Lanham version on a curved background, where GAB refers to the background metric. And this R here, this is the scalar curvature of the background. So what I will choose is a background of a so-called Schwarzschild black hole. Now, the Schwarzschild solution describing the Schwarzschild black hole was found just 1 year after Einstein published his field equation. So this was published in 1916. And this describes the simplest type of black hole, a spherically symmetric black hole, which is non-rotating and non-charged. So a black hole which looks the same from every angle. You can write down the metric for this solution like this, where m is the mass of the black hole. If m would be 0, then this just becomes what I showed you before, this flat metric for Minkowski space. But because we do have a black hole, we get these two terms here which correct the solution. Now we can follow this procedure I mentioned before, the conformal compactification, and compactify this spacetime and blow up the cylinder. And if we do this, essentially we have to replace the radial coordinate r and the time coordinate t by a set of new coordinates rho and tau, which are both defined in compact intervals as given here. In particular, I want to consider values for tau between 0 and 1. I want to prescribe initial data at time 0, tau equals 0, and evolve all the way up to 1, which covers a portion of sqi plus. Now, a picture illustrating this is shown here. The left-hand side of the picture somehow extends the picture I showed you before for Minkowski space. This is the region outside the black hole. And once again, we've got this boundary sqi plus, where all the gravitational waves eventually go to. Then we have I0, space-like infinity. And new is that we do have this boundary here, which is the surface of the black hole. It's the so-called event horizon. And anyone unlucky enough to ever cross this boundary is never able to come back and will, after a finite amount of time, reach this boundary, which is the singularity inside the black hole. That's where the curvature becomes infinite. Now, the full picture contains these two regions which are symmetric to the first two. So this here is what is called a white hole. It's somehow the opposite of a black hole. That's a region where anything can only come out and nothing can ever go into. And that's another universe outside, but it's assumed these two regions are just formal mathematical extensions, so they are perfectly fine from a mathematical sense, but it's not assumed they would be realized in nature. So likely only these two regions, the black hole and the exterior region, are physically relevant. Now I will concentrate on this yellow region here. So I want to solve the wave equation in this region. I want to prescribe initial data here and include space like infinity and also evolve up to Sky plus, the boundary where the gravitational waves are well defined. This boundary here is a characteristic of the system, so I don't need to prescribe any boundary conditions here. No information could propagate into the domain through this boundary. Now, after applying this transformation here, I can map this to the coordinates rho and tau, where I now prescribe initial data at tau is equal to 0 and want to evolve up to tau is equal to 1 here. And the cylinder, a point in this diagram, is now blown up to this entire line. And if you would include the two angles, theta and phi, you would get the full cylinder. Now, the corresponding wave equation for a function f that depends on all four coordinates looks like this. So it's a second order partial differential equation. And importantly, the angular derivatives appear only in this term in form of the usual angular part of the Laplacian. Now, because of this, we can separate our solutions. We can decompose into spherical harmonics and just have to worry about the coefficients for different angular modes Lm, which will only depend on two variables, the time coordinate tau and the spatial coordinate rho. Now, each of these modes, and I just for shortness of notation, I don't include these indices, has to satisfy this second order equation where only L appears here. So the equation is completely independent of M. And I always assume we make some fixed choice of L and M and then have to solve this equation. Now, in the first step, because we expect certain mathematical difficulties at or near the cylinder, we can study exactly that behavior. Now, in my picture here, the cylinder is located at rho is equal to 0. That's space like infinity. And in order to study the solution here at this boundary and in a neighborhood, I use this form of Taylor expansion about rho is equal to 0, where the coefficients are tau-dependent functions. And interestingly, if you plug this expansion into the wave equation, then you get intrinsic equations, just ODEs, for these different coefficients here. So without solving the problem everywhere in this domain, we can already learn something about the behavior at and near this boundary. In order to give you a feeling for how these solutions look like for these different coefficients, if we choose, say, L is equal to 0, the simplest angular mode, then the first function phi 0 is obtained by solving a certain second order ODE. So this will depend on two integration constants C0 and C1. And in general, we have this term logarithm of 1 minus tau, which would blow up as you approach this red point here, where tau is equal to 1. So in general, we get a logarithmic singularity. But we could try to achieve that this coefficient C1 is actually equal to 0. It turns out that's something that we can determine by a suitable choice of initial data. At this boundary, tau is equal to 0. The initial data are the initial function values and the initial time derivative. And it turns out the time derivative at this point is proportional to this constant C1. So if I would choose initial data where the time derivative vanishes here, then I automatically ensure that the corresponding time evolution for psi 0 would be regular. Now, if I do this, it turns out the next function in this expansion is automatically regular, but one order above, we once again get a singular term. It's a milder singularity because the logarithm is also multiplied by 1 minus tau squared, so a coefficient that vanishes at this point, but at least in the second tau derivative of this, which corresponds to a higher order derivative of the full function, will again be singular at this point. Unless we once again achieve that this term does actually not appear, if we make sure this coefficient is 0, and this coefficient is once again given in terms of something that I can read off from my initial data, so I can already decide by just looking at my initial data if the singularity will be there, or just fine-tune the initial data to avoid the singularity. Now this trend continues, and one can study in general the behavior for arbitrary angular modes L. If the first few of these functions are all regular, then the next one would generically contain a logarithmic term of this form, so we get singularities at various orders at this point. But it's always possible to suitably fine-tune the initial data if we want to avoid the singularities. Now here, this gives you an impression that you can repeat this analysis for other values of L and the different expansion orders, and you always find some conditions which ensure that the logarithmic singularity at this order is eliminated. Now, in order to study the solution everywhere and not just at this particular boundary at the cylinder, I use a numerical method, a fully pseudospectral time evolution scheme, where the basic idea is that the unknown function is expanded in terms of Chebyshev polynomials, and this is not done only in spatial direction. Sigma here is a rescaled spatial coordinate, but also in time direction. So it's a somewhat symmetric expansion, including both the space and the time directions. Now we have to find these Chebyshev coefficients, and we can do this by demanding that this approximation here solves the equation or boundary conditions exactly, not everywhere, that's not possible, but at a certain set of grid points, collocation points as shown in this picture here. So this particular choice of points is also referred to as Gauss-Lobato nodes. As you can see, they are a little bit denser at the boundaries and not quite as dense in the interior, and they're also constructed from Chebyshev polynomials. So by demanding that this approximation is exact at these points, I get an algebraic system of equations which I can solve using a Newton-Raphson method. And once we have these Chebyshev coefficients, I have approximations for my solution not just at these grid points, but actually everywhere, because I can plug into this expansion arbitrary values for sigma and tau. Now, in order to study how regular the numerical solutions are, or how accurate, and how this does depend on the presence of various logarithmic singularities, let me illustrate this for one family of initial data, where I choose L is equal to 0 and describe these initial function values and these initial time derivative values at tau is equal to 0. And that's actually a family of initial data depending on two real parameters, alpha and beta. And these allow me to control the regularity of the solution. Looking at this previously mentioned regularity condition, it turns out for any choice of alpha and beta, the first two expansion orders psi 0 and psi 1 are always regular, but the next one is only regular if I choose alpha is equal to 0. Otherwise, if alpha is non-zero, then psi 2 will contain a logarithmic term, and the magnitude of this term is proportional to alpha. And if I in addition choose also beta is equal to 0, then the logarithmic singularity at the next order disappears. So we can see how this affects the numerical accuracy. Now here you can see some convergence plots where I plot as a function of the number of Chebyshev polynomials or the number of grid points, my collocation points, the numerical error in a double logarithmic diagram. And you can see curves corresponding to different choices of alpha and beta. The green one has the largest value of alpha, where we get the strongest logarithmic singularity in this function psi 2. And you can see that if we choose just a sufficient number of grid points, so if we and it's still moderate grid points, then we observe still an accuracy in the order 10 to the minus 7. So even this somewhat singular problem can be solved with a reasonable accuracy. But then as you make this coefficient of the singular term smaller, the accuracy improves. And going from this curve to that one, where alpha is very small, and here alpha is exactly equal to 0, gives more than one order of magnitude in accuracy. So these methods are quite sensitive to presence of singularities. And if you remove the next singular term, then you gain about another order of magnitude and then get even highly accurate solutions where the numerical error is in the order of machine accuracy. And here, because these curves are approximately straight lines, we observe algebraic convergence in this double logarithmic diagram. This means that the numerical error is decaying with some negative power of the number of grid points. Okay, so far our analytical considerations have shown that as we go through the cylinder at rho is equal to 0, then we necessarily get some logarithmic singularities. But what happens if we approach the future boundaries chi plus along some other curve? So for example, if I would follow this green line, do we also get logarithmic singularities here? So far we only know they appear here at this point. Now, this cannot be decided analytically because then we would need to know how the solution behaves everywhere. But because we have our highly accurate numerical values, we can actually take advantage of this and give numerical evidence that we actually find singularities here as well. So for that purpose, once we have solved the problem numerically, just read often the function values along one such line corresponding to some fixed choice of the coordinate row, expand this in a one-dimensional Chebyshev series, and then it's well known the corresponding Chebyshev coefficient ck in this expansion will decay, and how quickly they decay depends on how regular the solution is or how well behaved the solution is. So by studying the fall-off behavior of the Chebyshev coefficients, we can determine how regular the solution is. But for different choices of the position of this green line, for different constant values of rho, I get these different curves here, where I plot the value of the Chebyshev coefficient ck as a function of the index k, again in a double logarithmic diagram. And because in a certain index range, this again behaves approximately like straight lines, and this is parallel to this straight line with slope -7. This is consistent with certain logarithmic singularities, because the theory tells us if the function would contain a logarithmic singularity of this form with some exponent s, then the Chebyshev coefficients in this picture should indeed fall off with straight lines with a slope given by this number here. So that's consistent if we observe a negative odd number. So we find numerical evidence. There are singularities not just here, where the cylinder approaches chi+, but actually everywhere on this boundary. Next, I want to comment quickly on a different type of initial value problem. So far, I have prescribed initial data at tau is equal to 0, which is a Cauchy surface, a surface that goes all the way to space like infinity. The question is what happens if we go even further back in time and want to solve a characteristic initial value problem where we provide initial data on a part of sci-. So in a corresponding picture, it looks like this. Previously, I've prescribed initial data here and solved the problem in this region here to understand the behavior near the cylinder and near future null infinity. But if we include this domain here, we can actually prescribe initial data on a portion of sci- and a second characteristic surface. So the idea is eventually we would be interested in something like a wave scattering problem, where we prescribe information about ingoing radiation, which somehow enters our space-time, and after some interaction in the space-time, eventually reaches chi+. So then we can work out how the data here eventually transform in information about, say, gravitational waves at chi+. If we want to solve this problem, we can first again study the behavior in our cylinder and plug in the expansion about rho is equal to 0 as before. Once again, we obtain ODEs, but they are a little bit different from the ones which we had before, because in the ODEs degenerates in a certain way as we approach sci- at tau is equal to -1. Previously, in the Cauchy problem, the ODEs for these coefficients were just regular second-order ODEs, where the natural initial data are the initial function value at tau is equal to 0 and the initial time derivative value. But here, because of a certain degeneracy of this equation, what we have to prescribe instead is, again, the function value, now at tau is equal to -1, but then the nth derivative value at tau is equal to -1. So it's a different type of mathematical problem we have to solve. And studying this problem, turns out this time we get in general logarithmic singularities of this form, both with a plus and minus sign here. So in addition to the singularities at tau is equal to +1, our singularities at sci+, we find similar singularities already at sci-. That means even if we prescribe regular characteristic initial data, regular function values on sci-, certain time derivatives will already initially develop these logarithmic singularities at the cylinder. And consequently, we can now study two sets of regularity conditions, conditions to remove singularities at tau is equal to -1, and again, the previous conditions for regularity at tau is equal to +1. These are also mathematically different from the regularity conditions we had before, because they tend to involve higher order time derivatives, which are not readily available from the characteristic initial data, because we just prescribe function values, but our regularity condition also provide information or need information about these derivative values. In order to actually work out these derivative values, we also have to study the behavior of the solutions in the vicinity of sci- in a neighborhood of tau is equal to -1. And for that purpose, we can again use a Taylor expansion, this time about tau is equal to -1, where the coefficients are rho dependent. if we plug this into the wave equation, we get this term first order ODEs for these coefficients phi n, and these phi n are just proportional to the time derivatives that we need to study our regularity conditions. One can solve this ODE and obtains this formula, which allows to compute the next function phi n from two previous functions, phi n minus 1 and phi n minus 2. So starting from the characteristic initial data, we can work out these functions phi n in this expansion. So we get now a slightly more complicated strategy to determine already by looking at the initial data how regular the corresponding solution will be after the time evolution. Firstly, we have to specify some initial data. Secondly, we use this iterative formula to work out these functions phi n. These are proportional to the initial time derivative values, so we can specialize this to rho is equal to 0 to the cylinder, and that's exactly the values that we need in our new regularity condition, so we can now test how regular the solution will be. Or the other way around, we can use this approach to design solutions which have a prescribed degree of regularity. Just start from a family of initial data, depending on a number of parameters. And while you go through this analysis, just adjust these parameters in such a way that the first two regularity conditions are satisfied. Then you can eliminate the highest order logarithmic singularities. Now, as far as this characteristic initial value problem is concerned, so far I've only studied this analytically, but the next step will also be to solve this problem numerically as well. Okay, this is what I wanted to tell you about this wave equation on a Schwarzschild background. Let me just summarize. We've looked at the initially 3 plus 1 dimensional wave equation, 3 space dimensions, 1 time dimension, but with decomposition into spherical harmonics, we can actually reduce this to a 1 plus 1 dimensional problem. So we have to solve for functions depending on rho and tau, our two coordinates. These equations tend to degenerate on the cylinder. We get intrinsic transport equations. So without solving the problem everywhere, we can already analytically determine at which orders we will get logarithmic singularities. And we obtain regularity conditions which allow us to even design initial data where we get a certain degree of regularity. And these singularities, which we analytically observe on the cylinder, are not restricted to the cylinder, but from our numerical investigations, we also find numerical evidence that we get the same type of singularities everywhere on Scri+. And finally, I've mentioned the characteristic initial value problem, which is mathematically a little bit different. Now we also need to study solutions in the neighborhood of Scri- in order to even obtain the required initial data for the cylinder ODEs and to determine the regularity, because our new regularity conditions require these time derivative values. Okay, that's all from me. Thank you very much.
Thank you, Jörg. Are there any questions for Jörg? I see. We'll have to ask a first question. Well, for me, I will probably ask just some question about the thing that you plan to do on actually checking what you just developed with the numerics. Can you just tell me a bit more about how you will start with the numerics for this problem, for this initial value problem?
Yes, so the characteristic initial value problem will be somewhat similar to the problem I solved first. We already have the numerical results in the Cauchy problem. So essentially, instead of just looking at this one domain, I now have two domains. And one technical detail is that it is useful to use two different sets of coordinates in these regions as plus and as minus. And then I have certain transition conditions here. So very similar numerical method compared to the other one would allow me to prescribe then initial data here and here and solve in this region in the first step. And then I can translate this into suitable initial data for the other domain, and then essentially repeat what I have done before and solve a Cauchy initial value problem here. So it's a relatively straightforward extension of the previous numerical method.
Okay.